Okay, welcome to lecture 16. So we've just finished our named continuous random variables, and now I want to look at something that sort of puts a load of these together, a thing called a Poisson process. So what we're going to do is we're going to have some process that we're following. We start at time 0 and we look, and every so often you're going to get an instantaneous event. Let's assume, for example, it's arrivals at a call center, accidents, something like that. And all we're going to assume at this point is that the time between events are exponentially distributed and they all have the same rate, which we'll call lambda, and they are independent of one another. We're going to have some extra notation. So first of all, xi will be the time between the ith minus 1 and the ith event. N of t will be the number of events in time period t. And st is the time to the tth event. Sorry, to the nth event. Well, that should be, let me just change that. That should be an n. So we've got this thing called a Poisson process, and we've got these properties. But before we start, let's have a visualization of what this looks like. What we've got is we've got time along here. We'll start at 0. And every so often we're going to get an event. They're not evenly spaced, these are, stochastically spaced. And this time here we'll call x1. It's the time to the first event. This one is x2, time to the second, and this is x3. Other things we could measure this process is we could take a time point here, t, and we could count the number of events here. So in this case, nt would be equal to 2. And also we could look at the time to an event. So this here from 0 is S3 is the time to the third event. First thing to notice, let's assume that we look between 0 and 4 and we count our events. So we have 1, 2, 3, 4, 5. First of all, notice in this case that this is the time to the fifth event, S5, is less than 4 in this case. Yeah. This is also equivalent. You could actually have, some extra events here. But you know that in this case, because the fifth event was less than 4, the number of events in this time period 4 must be greater than or equal to 5. So this interchangeability, you can look at the time to the rth event, or you can flip that around and count the number of events in time. And because the time is a difficult distribution to deal with, we often do the counting because the counting's nice. So given that, let's see what they have. Well, the first thing is, if you look at a length of time t and you're modeling the number of events, that has a Poisson distribution, hence the name Poisson process. How you get the parameter in that, you take your rate, lambda, you times it by that length of time t, and that will give you the expected number of events, so that will be your parameter you put into your Poisson. The time to the nth event, we are adding up a load of independent exponentials. And last time we discussed that this has a gamma distribution. In fact, it's that specific gamma distribution we call the Erlang, where we've all got the exponential has the same lambda and we're adding them up. So we've got a gamma. Often we prefer to work with a Poisson, it's much nicer. What sort of properties does it have? Well, the first nice thing is if you take two time periods that don't overlap and you're counting how many events in each, these are independent random variables. So that makes calculations a lot easier. Oh, sorry, that's the independent one there, I flick 2. The other one is, I don't care when I start counting. If I started at 9 o'clock looking at a call center and I have a Poisson process and I observe the number of events in an hour, so between 9 and 10, that will have exactly the same distribution as if I started at 12 o'clock and look between 12 and 1. So the idea is what we call shift invariance or time invariance or homogeneity, is the distribution doesn't depend on the time I start looking, just the amount of time I look for. And in these cases, it's a Poisson distribution. So let's do some questions. We've got a customer's phone. It's a Poisson process. We have a rate of 3 per minute. Do be careful with your time units. Notice this is all about per minute. And so if we change our question to be seconds or hours, we need to adjust accordingly. So we need no calls to arrive in the first 2 minutes. So I'm going to add some notation to just check we get the time right. So I'm going to let NAB be the number of events between time point A and time point B. So the first one is we want the probability that the time between the start and the first 2 minutes, so between 0 and t, equals 0. As I said, because of time invariance, this is the same as the probability n2 equals 0. I don't care that I start at time 0, I just care that it's 2 minutes. So this is time invariance. Well, that is going to be what? That is going to be e to the minus 6, 6 to the 0 over 0 factorial. Why? Because n2, the number of events in 2 minutes, is Poisson. We take the rate times by the amount of time. So that's Poisson 6. And this is my probability mass function for a Poisson with lambda equals 6. I could also do this by d plus 0, 6. Next question. The first call arrives after 2 minutes. So what have we got here? Let's draw the picture. Here's my 2 minutes. And here's my first call, sometime to the right of that 2. So within here, I have no events. So the probability that S1 is greater than 2 is equal to the probability that N02 equals 0. And we've already done that calculation. It's that there. Cool. Next one. So we've done this one, we've done this one. No calls arrive in the first 2 minutes, and at most 4 calls arrive between 2 and 3. So let's draw our diagram again. In the first 2 minutes, is that right? Yep. We've got none, and then in the next minute, we have less than or equal to 4. So let's write that in our notation. That's the probability that between 0 and 2, we have none, and between 2 and 3, we have less than or equal to 4. Well, notice this time period, okay, they meet at 2, but they don't overlap. So they're independent, so I can write this as the probability that N02 equals 0 times by the probability N23 is less than or equal to 4, because they are non-overlapping, so independent. Well, the first one, we know this is the probability of N2 equaling 0. What's this one? Well, we can use time invariance and say this is N01 is less than or equal to 4. So again, time invariance. So this one we know is, d plus 0.6. What's this one? This is the probability that N1 is less than or equal to 4. So we've got less than or equal, so that's a P Poisson. We want it to be less than or equal to 4, and the rate is going to be 1 times 3, so 3. The fourth call arrives within 30 seconds of the third call. So what have we got? We're going along. We've got here's our third one, and here's our fourth one, and we know that this time is going to be less than 30 seconds. Well, this is the time to the fourth, so it's x4. So we want the probability that x4 is less than, well, everything's in minutes. I better convert 30 seconds to minutes, so that's half a minute. So we're going to integrate from 0 to 0.5 our exponential, which is going to be 3e to the minus 3x dx minus e to the minus 3x from 0 to 0.5, which is 1 minus e to the minus 1.5. Or you could use that by using px 0.53. That's good. The time to the fifth call is greater than 2 minutes. So here's our 0. We've got our fifth call, 1, 2, 3, 4, 5. And this is greater than R2. So we want S5 is greater than 2. We want the probability of that. Well, we know that that means that the number of events in the first 2 minutes must be 4 or more. But generally we know that the number of events must be less than 5, because we can't have the fifth call in that first 2 minutes, otherwise we haven't got that it's after 2 minutes. Which, as I said, is equivalent to the probability that n2 is less than or equal to 4, and this is P plus for 2 minutes, so it's 2 times 3, so 6. Done. So there you are. There's your first sort of big major process that we've modelled, and to do that we model it using exponential, Poisson and gamma. Next time we're going to start looking at how we find the distributions of new random variables. See you next time.